Hi, everyone. Welcome, Azure Cosmos DB Live TV. Welcome, and thanks for joining us this week. It's been a while. We've kind of taken a little bit of time off over the last few months, but going to be ramping that up again, and we're going to ramp it up hardcore with our friend Sergey. How are you, sir?
Hi, Mark. Nice to see you again. It's been a
Yeah,
while.
it has been a while. Definitely good to see you. We're going to talk about something. I don't know if people realize this, but we've got a .NET SDK, a Java SDK, we have a JavaScript SDK, we have a Python SDK, we have a Go SDK. We've been kind of working on in secret. We're going to talk about another SDK that probably not a lot of people are familiar with, but if you've ever tried to write large, vast quantities of data to Cosmos DB, this SDK, I think, should be your best friend. Wouldn't you agree, Sergey?
Absolutely.
Yeah.
To me, this is I wouldn't call it SDK, I would call it a connector
Yeah. Okay.
because it's technically based on Java SDK. But this is a must technology to have when you task to do large data volume writes into Cosmos DB to achieve the high throughput and to be able to parallelize at scale and control it, which is also most important. That's what we're going to talk about too.
Yeah. So our Spark v3 connector is what we're going to talk about today. And as Sergey mentioned, this is definitely your friend and something you want to look at if you're trying to ingest large quantities of data. We've been working on this thing for quite some time, and we've got our new v3 version of this thing out, and it's got at least what I consider critical cool new feature, which is the throughput control on there. Are you going to show us that by chance in the
Yeah,
config?
absolutely. We're going to show throughput control. We're going to show some other really cool features in the Spark connector, and we're going to start talking about best practices in general. Like basically, what are the best practices for large data set migrations into Cosmos and how to control them. Some nuances around how to use SDK and some sort of hidden features which are not necessarily popularized or spoken about at the high level. So like our agenda for today, we'll start with best practices in general, kind of like to reiterate the fundamentals of Cosmos DB and how we can leverage it. And then we're going to focus on Cosmos Spark Connector evolution, basically what we had prior, why it was great, but it was good, wasn't great, right? So there was room for improvement. And then we're going to dive deep into features of the new Cosmos Spark Connector. And we'll do some demo snippets to show in real life how it looks like and why we will use one feature versus the other, etc.
Cool. Well, this looks like a good agenda, and I think you're basically covering all the big things here. So
Yep,
yeah, let's dive right
absolutely.
in.
So um, let's first look at the best practices for large data set migrations and bulk loads in general, right? So as we all know, Cosmos DB is a distributed database, and the data distribution is based on physical partitions under cover. And we know that max partition size right now is 50 gigabytes. When we're doing the bulk data load in Cosmos, what we want to do, we want to minimize number of partition splits and data migrations, which will be competing for the same resources when you're doing bulk operations, because the goal of bulk operations in parallel is to optimize the data load in terms of let's use all the resources from CPU network IO possible to achieve the best throughput possible. In order for us to do this, we want to pre-create number of targeted physical partitions based on the data size load, projected data size loaded into Cosmos to conceptually avoid the partition splits and data redistribution. Even though Cosmos will do it, this will take away from the resources needed to do the load and also create some other imbalances. In order to do this, normally what we would recommend is take your total data size in gigabytes based on your JSON, like average JSON file size or document size. and divide it by targeted data per physical partition. What we normally recommend is use 45 GB per partition because there will be some indexing overhead, potential data growth, etc. So like you don't want to load data up to 50 gig and then start splitting it right away. Doesn't make sense. So I normally use 45 GB because this will give me enough headroom for indexing and other stuff.
Yeah, indexing could add some additional storage there. You have it's an interesting note about just accounting for bloat due to JSON. Do you have a rule of thumb you use converting between, say, CSV or Parquet into a JSON format, or?
I've seen it really depends on the on the file structures.
Yeah.
It's definitely going to be times smaller. I mean times higher than let's say if you have JSON file in 1 gig, CSV file in 1 gig, JSON will probably be like 3-4. Parquet probably even higher. My recommendation would be take a subset of data, or like let's say if you need to load 100 files, take 2, load it and measure, and then use extrapolation based on this, because this will give you the better accurate measurement, because you may be few times off in your estimation if you just do paper exercise.
It's solid advice. I mean, and what I generally tell people is, look, if you want to know the answer to your question, you've got to have to do a little test and measure to really know. So yeah, makes sense.
Then next step is calculate number of RUs optimal for your dataset ingestion based on size. And the rationale here is that when you do large dataset loads into Cosmos, likely your RUs will be driven by the size first before the workload comes. And if it's the other case where it's a high storage, low throughput, we also have a program for this, but you still need enough RUs to load it fairly accurately and fast in terms of like achieving the most recommended throughput. I'm going to show you a little later why I'm saying this. And then we usually use 2 factors here to do the estimation, depending on mode of provisioning of throughput. For auto-scale or shared database throughput, the rule is it's 10,000 RUs per physical partition. That's the max limit. For manual throughput, it's 6,000 RUs per partition. I honestly do not know why we have a difference, but that's just historical difference, I guess. And then you just use that those 2 factors in formula. And then at the end, you calculate based on those 2 throughput per second, based on the RUs of write RU for average doc size, assuming that you tune your indexing policies, etc. And then you can use this to calculate your total time in hours based on this. Why I'm calculating it in hours is because while we set up and measure RU per second, we bill RU per hour. So from data load perspective, it's a lot of time. Hour is a good aggregation level because we pay by hour. So like if our goal is to load large data set, it won't be a difference whether I load in 15 minutes to 30 minutes if I have to spend twice more RUs, because I'm going to build for max RUs used within the hour anyway. And all those things are referenced in our documentation. I have a shortcut reference link at the bottom, which I strongly recommend. There is more details there. Now let's look into how it's going to look like in practice, all those recommendations. So I took an arbitrary data set, 1 billion records of average document size 20 kilobytes, and I measure the write RU creation for the document as 11 RUs. In that case, I'm actually only indexing ID to measure it. So with that estimation, my total data size would be 20 terabytes. And based on this, if I use 45 GB per partition, I need 444 physical partitions. And then once I know this, I can use it to calculate how many RUs I need for manual throughput with 6K per partition, for manual throughput with scaling up to 10K RU per partition, and then also auto scale with 10K per partition. And then at the bottom, I'm calculating the throughput of writes per second, estimated throughput, and also estimated total load time And then I'm going a little step further. Let's put the dollar number to it. Let's estimate how much it's going to cost us to load the data, right? So like in per hour cost before we can scale down to whatever minimum we can afford. So with that case, with manual initial load with 6K RU per partition, we will load in 1.2 hours, and it's going to cost us $426. But with manual scale up, basically creating those 444 partitions using 6K and then scaling up to 10,000 RUs, we can double the throughput, load it in less than an hour, and it's going to cost us only $355. So from that perspective, it may be counterintuitive, but creating the container with 2,667,000 RUs and then scaling it up to say 4.4 million RUs and loading the data, we can achieve the load within an hour. So we're not going to spill into second hour, and then we can scale down earlier and saving some money actually on the load. Obviously, out of scale will achieve the same throughput, but cost us higher because of the out of scale cost factor. So for one-time large loads out of scale doesn't make sense. Manual is technically better, right? The second table highlights that if you scaling down you provision the 444 partitions based on the RUs, and then you scaling down those RUs, you can, it doesn't really buy you anything. Yes, you're going to take load higher, but the cost is still going to be the same because of the cost factor, right? So you have less RU, but it's take longer to load. So net, it's a zero-sum game.
There is a limit to this, though, right? And I just want to call this out because you're kind of demonstrating kind of the cost of time here with respect to how long you have to be at certain throughput to ingest your data. What I want to make sure people don't walk away with thinking is, oh, I've got like 50 gig of data and I really want to get it in fast, so I'm just going to provision 1 million RU, ingest all that data, and then drop it back down. And the problem there is there's a limit to how much you can scale back down after you've done a big scale up, and you have to kind of balance these two things.
Correct. And that is the reason why I always start with number of documents, document size, and estimated data size. Because the key here, you said that if you only have 50 gig of data, with 50 gig of data, I only need one physical partition, means that from data perspective, my threshold should be 10,000 RUs maximum, right? And I would estimate, so all that estimation is, what is the optimal RU load based on the data size itself? Because data size will drive down the minimum scalability when we're talking about terabytes of data, right? So like and then if you need to load it faster, like we're kind of like telling you that regardless how much data you have, if you size your physical partitions optimally, you can load within a couple hours, right? So like this is just logic here. Obviously, if you have to scale it down for the workload, the formulas and minimum still applies there. The formulas here is the scale down would be maximum of RU provision divided by 100 and maximum size divided by 10 RU per gig, right? So or 100 RU per gig for other scale max, which is
I had Deborah on. Oh, this is a few months ago, talking about kind of best practices for throughput, and she kind of walked through, like, if you're at this amount of throughput and you need to scale out, this is what happens to the physical partitions behind the scenes. And I can see it reflected in your data here, where you've got initial scale out at 6K. And the reason is because we apply a different heuristic to how many physical partitions we provision if it's done initially when you provision it, because we assume that you're going to ingest a bunch of data after you create it, and we want to reduce the number of splits because it can affect latency if you're doing high volumes of writes. So to reduce the amount of splits that happen afterwards, the threshold for when we do the split is at a lower level, which is more like that 6K versus I think like 8K or higher if it splits after the fact. So if you scale it up. So Yeah, this is great. I like this, and this is I should steal this and give it to people because I get this question all the time. Like, I've got this amount of rows or data. Is the size of my items. How long is it going to take me to input this, and what throughput should I use? So this is very handy. Very, very cool.
All right, let's move on. So the second or last part of the bulk load optimization is optimizing the indexing strategy. Use custom index policy to reduce write RU impact, amplification, and customize the index policy based on final query wait patterns. Basically, if you need to load terabytes of data into Cosmos, what I've seen is customers try to either disable index period or only index ID and then load it. And then after that, they start updating index policy. But index policy update, while it's online async operation, will still take time. So if you already know what those are upfront, put them right in index policy. Maybe it will take a little longer to load, but it will minimize that overhead, because in order to rebuild the index for a large data set, it will, like, you likely will need to scale up again and scale down. So it will reduce that micromanaging of the update in the index policy as well. All right, so let's look to, I want to highlight the index policy update on large data sets. So I took 5 million data set, and I was loading it with default index policy. And you can see that for the same data set, I was able to achieve about 350 requests per minute. Those are aggregation numbers. Now, if you look into loading the same data set with only index and ID out of 20-something properties, I almost double my request throughput per minute. So instead of 350, actually more than double, I was able to achieve a little higher than 800,000 requests per minute. So this will give you ability to load much faster, and you can actually see it with the timing as well, right? So like the loading with, in that case, only ID took 8 minutes, where loading with default index strategy took 21 minutes, over 21 minutes. So that's basically, this is a practical benefit of customizing index policy and only indexing the attributes we need. So let's move into Spark. So why Spark for Cosmos bulk loading? And outside of Spark, we have other tools which also do bulk load. We have native bulk API or batch API we had within the SDK for both Java and .NET. We support bulk APIs were incorporated in both Azure Data Factory, Data Copy, and Data Flow from different SDKs, and the original Cosmos Spark 2.4 connector to do those efficient bulk loads. But all those technologies, while they natively have the same concept behind the scenes, they execute parallel micro batch loads to minimize the number of round trips to the backend in Cosmos, and they have they are Cosmos aware from partitioning perspective, so they can distribute parallelize that workload more efficiently to distribute the data for both reads and writes. The limitations were conceptually around control plane operations, right? So like there was no way to create, at least from Spark perspective, to create or adjust Cosmos DB throughput for bulk load within Spark job itself. It has to be external trigger incorporated as a pipeline, a little harder to coordinate. There wasn't great fine-grained throughput control, and that was, to me, the biggest gap in the older connector. And this is especially important. While it's not as important for initial bulk load when you're doing like your container is idle, you don't have any APIs, but when you did the initial load and then you had to bootstrap read APIs, but you still need to do delta loads, you you need some control to make sure that you don't use all the resources on Cosmos side, to leave some resources for APIs to serve. And that was always a challenge, because not with everything being near real time online, we have less and less windows to do those delta bulk loads. And with the data volume growth, a lot of times they are pretty significant on its own. And in addition, there was challenges with customizable retries. There was not a lot of exposure to what we can customize, what we actually retry, and how long. And then other concurrency control mechanisms for upserts. So based on all those limitations and a few other things, I'm glad that we, and this is your mark and your team delivery, I'm glad that you deliver Cosmos Spark 3 OLTP connector, which is based on the new Java version 4 SDK for Cosmos DB, and it's using all those great features and more coming to solve those challenges. And let's look into those in detail. So the first thing is, there was a lot of documentation on using Spark 3 OLTP connector with Databricks. Most of the examples on Databricks. So in the talk today, I want to highlight how can we use the same connector, OLTP connector, in addition to our HTAP OLAP connector with Synapse Spark, because we do have integration. We can use it. It's actually sort of built in, and it's great to be able to interchange both of them, right? So so the first thing is Cosmos Azure Synapse Spark workpools runtimes for both 2.4 and 3.1 and 3.2 have Cosmos Analytics Spark connector jars built in. So they are built in the runtimes for each, and basically each version has its own runtime. You can override those default load in specific connectors with specific jar files. Basically, get the jars and use Synapse Spark package management to upload the jar library and override it from default. The two options to connect from Spark to Cosmos: the classic OLTP, where you have to define account endpoint, account key, database, and container. And if you use the Synapse Link service, which is now another option with Synapse and Cosmos integration using Synapse Link, once you have Synapse Link defined, you can use actually container scope, because Synapse Link has a database scope built in within. So you can abstract your endpoint and master key security. You don't have to use key vault to store the secrets and trust, and use Synapse Link built in, which is also great. So both options are available. Synapse Link would be great to abstract the security part of it and just scope the link service and container down the road. Now, migrating from Spark 2.4 to new Spark 3 connector. So there was several questions like from different customers who used to do it. And the big driver for those migrations is actually Spark 2.4 retiring. It's basically end of service, I believe, is July 2022. There was a big push to migrate old Spark workloads because there is already Spark 3.2, so the 3.1 is sort of the mainstream now. New connectors support both 3.1 and 3.2. That capability is there. The other conceptual differences is there is now separate data sources for different streams of data. For example, to write data from Cosmos transactional store, we have cosmos.oltp. For reading data from change feed, we now have cosmos.oltp.changefeed. So it's actually clear separation, clear feature differences, and clear parameter controls. And then for structured streaming, there is biggest difference is a different checkpointing with a new Cosmos data source, Cosmos OLTP. For streaming, now the proprietary checkpoints replaced with native Spark mechanisms where possible. Basically, native Spark offsets checkpoint resume within Spark, which checkpoint locally within the cluster. and give you more transparent behavior with other Spark streaming technologies and solutions. So you can expect the same sort of behavior when you use it with Cosmos. And I included the link for Spark 3 migration, and I can show you what it looks like from comparison, where you can basically map older Spark 2.4 configuration parameters and map to the new Spark 3.1 and above configuration parameters, and some notes as far as the nuances, et cetera, where it's deprecated or not used anymore. So it's really helpful to use this helper documentation to go over when you do the migration.
I got a question from a viewer here. Says, I see there is a limitation that RBAC is not supported with Synapse Link.
Yeah, we can quickly talk about it. RBAC is on the roadmap. It's actually actively worked on and sort of the next thing coming. And the biggest delay was actually on Databricks team, I believe, at least based on the feedback that they are working on that integration to provide this. So basically Databricks Spark to support Azure Active Directory integration to allow us to use it native RBAC, which is part of SDK.
Yep.
So this is coming fairly soon.
Yep.
All right. So let's look next. So Cosmos Spark Connector, how bulk ingestion works behind the scenes. So in Spark data frame, usually partitioned based on source data set partitions. And for each partition of source data, Spark will create independent tasks. Our Cosmos OLTP data source will create singleton Cosmos client instance for each executor driver node. So the client instance will be shared across multiple tasks, but each task will have one bulk writer to execute in parallel. So that each bulk writer will buffer data memory for each physical partition in Cosmos and then flush it basically to minimize number of round trips and optimize that throughput. So this is really good at scaling for most of the use cases, with only exception for very large workloads where you're looking like above 100 physical partitions, 5 terabyte plus, because it may create client-side overhead. So with that, for that type of loads, you may look at custom repartitioning and batching, and we provide the feed range for partition key value basically to minimize a number of those bulk writers. Now, choosing the right Spark cluster size. That was a lot of misconception, like how big my Spark cluster should be for bulk loads. The rule of thumb here is that one Spark executor, one core, can easily saturate 3,000 to 5,000 RUs. Knowing that Cosmos limitation for partitions, for physical partition, is 10,000 RUs. So recommendation is to use 1 or 2 executors. Basically, I would say if you provide 5,000 less are used for physical partition, it's 1 executor. If it's above, 2. So that's easily, like, you can use this as a sort of the rule of thumb to estimate how many executors you need, and based on that, define your Spark cluster based on the targeted load, number of physical partitions in Cosmos. Now let's look into new Spark 3 OLTP connector new features. So there is several new features which are really excited. One of them is catalog API. I mentioned in the limitations of the old connector, it didn't have ability to create containers or set RU in the containers. So now we have basic ability to execute Cosmos DB control plane, create drop container commands. I mentioned, and we can preset the RU settings as well for bulk load. And then the biggest change is probably within the connector itself is improved throughput control and additional partition configuration parameters. The throughput control is key for ability to fine-tune the load, especially for delta loads, and manage the resource sharing within Cosmos between the ETL, which is usually very resource-hungry operation, and the regular operation. to minimize the retries and latency spikes. We also expose some Cosmos retry policy parameters and new write strategy options for implementing bulk update deletes with optional concurrency control detection, which were not available or not possible with the Spark and Spark connector. And I'll show you the differences, how we could have done it with old connector and it's still valuable, and why the new one is better. So let's look at each one of them, sort of drill into each one of them with examples. So the first feature is catalog API. So to register, all you have to do is set catalog, Cosmos catalog, config setting, and then after that you can use Spark SQL to execute Cosmos DDL commands, basically to create database, create table, and then define table properties like partition key, scale, like basically in our use, whether it's auto scale or manual throughput, and then define index policy. And there is options for only system properties, means ID, or you can define a custom index policy. Basically, this could be like your JSON payload for custom index policy and preset it. And then the same catalog can be used for creating views on top of the loaded data, which is actually very interesting for actual queries. And then obviously for dropping, right? So we can drop table or show tables just to use them, both of them using the same Spark SQL. To show this, let's look into examples. So this is my sample Spark notebook where I'm using the Cosmos endpoint and master key to query from Key Vault. And then I'm defining basically this is my catalog initiation. And as I said, when my session died, let me restart it real quick.
Hey, Sergey, just to follow up on that question, you meant Synapse for support for RBAC, right? Not Databricks?
Yes.
Yeah, okay. That's what I thought. There was a follow-up question. So you said Databricks, and I think you confused.
Oh, you mean the
RBAC control?
The RBAC. So the RBAC control is actually for Synapse, but remember that OLTP connector is actually generic Spark connector. So from that perspective, we need to be able to support both, and that's what it's waiting on.
I see. Okay.
Still starting. So basically, I'll rerun it later, but the difference here would be that when we initialize the Cosmos catalog for using the regular account endpoint and the key for OLTP connector, we would pull them from, say, Key Vault to the secrets. And if we use the link service, we just use this link service to initialize it as an alternative way to do it. Once we initialize it, then hopefully, yes. So let me just rerun it. Now we can actually go and run all the create statements as Spark SQL, and they should be creating my database and different containers in my account. Yeah.
I've never seen SQL DDL used to create Cosmos resources. I had someone ask me a question the other day. They were like, hey, I come from like a SQL server background. What's the DDL script to create databases and containers? I'm like, dude,
there you go.
Here's an ARM template for you. You can go use that. But looks like this, if I wanted to, I could just use Spark connector and go back to my old ways, I guess.
Yeah, well, this is still limited. It doesn't give all the flexibility, but this is another feature on the roadmap to sort of keep growing it, because with parameterized notebooks, parameterized Spark jobs for ETL, from ETL perspective, there is a big need to create something, alter something. Let's say for ETL, we need to scale up existing container We can easily parameterize that scale up parameter, like basically what is our U needed for load, and then scale down if we're not using auto scale and we want tight control without those external dependencies and external before the pipeline executing job, I need to do this. After I need to do this. If my job fail, I still need to do this. So there is value here, and
Yep.
that's what we're looking to improve.
Yeah, it totally makes sense, right? You're doing some ETL. Chances are you're going to need to create some staging table or do something or whatever.
Yep.
All that stuff you just said. Yeah.
Yes, and then now let's go back to our deck. So one other change in Spark 3x is in the original connector, it was possible to let Spark to auto-generate ID column values. And within Cosmos, we need that ID column in a data frame to either preset it explicitly because partition key ID give us a unique key, built-in unique key constraint to uniquely identify the document. With new connector, we require now to pre-populate the ID in the data frame by ourselves, so we don't allow that auto generation. And there is a sort of reason behind this is, and this is also kind of coming from the SDKs themselves as Java SDK evolved, right? So in older SDK, we used to allow auto generation. Now we say we don't allow it as part of SDK anymore because it may create those hidden conflicts where the UUID can create a conflict, potential conflict. So within Spark, what we want to do when we basically use simple UDF to do the UUID generation for data frame, and basically like we have UUID UDF, and then we add the column for ID using that UUID UDF. But at the end, we want to do a persist to Spark, and persist will guarantee that that ID generation is persisted within data frame as a column, and will not, like when you actually do write, it will not have some random conflict. And sort of the same thing would be recommended to do if you do the bulk load natively. Yeah, and my notebook has the same code sample there because I'm using it as part of the load. When I read the data, I'm actually using that UUID generation and adding that with column ID. And then I'm adding also the inserted, basically inserted timestamp to define when I insert the record. Now let's go next, retry policies. So I mentioned earlier that the new Spark connector has more control of what's retried and actually clearly define what we're retrying. So what we retrying in Spark is all transient errors, means the throttle requests, 429s, network timeouts, any recoverable service errors to retry automatically. Any non-transient errors, for example, bad request, 400 error, when the value of ID column is invalid, which wouldn't be recoverable by retries, we result in Spark job failing. So basically, we want to fail the job instead of silently accept the error and move on. We also now a lot more clearly defining the unique key constraint policy violations, which is 409 error in Cosmos as a unique document conflict. And those are differentiate based on the different write strategies. Now that we, for item overwrite, conflict due to unique key violation will result in error. So if you're trying to upsert or insert item with item override strategy with the same partition key ID, will actually fail the job. For item append, unique key conflicts on PKID or any unique key policy constraint violation will be ignored, and those records will be basically skipped and not result in Spark job error. This is done to give flexibility for if you say, I have append only type workload, and if I have duplicate data arriving, I'm going to simply ignore it because I do not want to fail my job, and I want to ingest everything else. And this give you a little more flexibility what to do with the conflict resolution based on the unique constraints. Now, a new Spark 3x feature is JSON serialization settings. So by default, Cosmos OLTP connector will always create a JSON property for each column and data source, even if the value is null or like empty string or zero for number. If you prefer not to create those JSON properties for those empty fields, for example, you read in the CSV file and it has many, many columns, and you have nulls or empty values for the columns, because null technically not stored like in a relational database when it was extracted. You have options now to figure out what to do when you write the data into Cosmos. So basically, if you logically do not store the values for empty attributes, you can basically skip them. And we have 4 different options here. Always means that basically always serialize it. Non-null means no JSON properties will be created for explicit null values. Non-empty means non-empty values will be for empty string values or empty arrays, and then non-default will be skipped, not just for null empty, but also if the default value is 0 for numeric properties. And this will give you also another flexibility into how to write data from data frame, which is sort of the structured table, into JSON, and have that flexibility of formatting the writable data into Cosmos. Next feature is throughput control. This is my favorite feature by far in the new connector. The new connector for Spark has an improved throughput control functionality, which allows better control for bulk load and better RU sharing across between ETL and the regular operations. So the way it works is it requires separate checkpoint container, which can be shareable by multiple jobs to store and read those per executor records, and then adjust throughput using the feedback loop to avoid overload and retries. That container defined as a Cosmos catalog throughput control, where you define the sample database, and then it has to be partitioned by group ID. Usually the auto scale throughput 4000 is enough. And most importantly, that container has to have default TTL -1. We want TTL to be enabled on that container, otherwise it may overgrow too much. So we want the data to be purged after the job so we don't overload that. And at the bottom, there is sample configuration for throughput. Basically, you enable it with throughput control enabled. You define the throughput control name, which could be unique per job. And then you have options to define either target throughput threshold as a value, like a percentage value or factor, or a hard value of the RUs. And then you would provide the database and container for throughput where those checkpoints will be persisted. And the way it looks in the code is this is basically example of the write config, where I'm using the write strategy, item override, bulk enable true, and then throughput controls. And then at the end, I'm gonna just basically use it format OLTP mode append and use those write options.
So the 0.90 is 90% of throughput provisioned?
That is correct, yes.
Okay.
0.90 is 90% of total throughput will be sort of dedicated for that workload.
Got it. Okay.
I did 2 tests. One is doing the load without throughput control, and one did the same load with throughput control. So let me show you the examples. So this is example of the load of the same 5 million records without throughput control. Basically, we finished in 4 minutes, 9 seconds. And you can see that out of 5 million, almost 1.5 million were retries. So, and the retries, if you look at the time, they were stacked pretty much throughout the job time, right? So basically every second, every minute, there was a significant amount of retries up to 400,000 per minute.
Were
Now,
these retries that you handled, or were these silent retries in the SDK?
Those are silent retries, which handled by SDK, by Cosmos Spark connector. So that was like when I talked about retries that we automatically handle throughput, like basically throttle 429 errors. Those are the ones which were handled automatically. Now, if we use that throughput control, which I showed in a sample as 90%, the job finished in 7 minutes, 58 seconds. And out of 5 million, only 3.8, 3.9 thousand retries total. And you can see that retries only happen as a short blip at the very beginning of the job, and there was no retries when the job kind of like started and settled in its own control. And this is really the benefit. If we look at this, let's pretend that we're doing the daily loads, and during the day, let's say intraday loads of significant amount of data into our Cosmos DB, while we're serving that Cosmos DB by read APIs. What's going to happen in the previous job here, when we did not have throughput control, because the retries kind of like span across the full load time, we would be constantly having the retries on the APIs itself, because they all will be like, we basically maxed out their use. We all would be competing for the same resource. If we're using throughput control with some percentage, we would likely have really short spike of the retries at the very beginning, and then we'll settle at that 90%, and then we'll have our budget for read APIs, and read APIs will not exceed the retries. We'll have that SLA guarantees, which we normally provide for all the reads.
Does Spark Connector give you the ability to write your own retries? Let's say you go over the, whatever it is, 10, I think 9 or 10 retries we do silently through Java SDK. Is there a way I can create an exception block and catch up unhandled 429 and then apply just like I would in the SDK, I can get retry after out of the header, response header, and then retry.
We expose configuration parameters for retries. Basically, you can control how many times you want to retry before you fail. So you cannot capture retries exceptions by itself. You can capture the failure after the retry, after you exceed the sort of built-in retry policies, because Spark Connector by itself is a wrapper on top of the SDK.
Right.
So if you want to build sort of very custom retry logic, what you can do, you can in Spark, you can inject the driver itself, create your own builder, and basically create Scala code to inject Java SDK, and then build your own custom retry policies. So if you want to do it, yes, you can, but people did it for other things, but not necessarily for retry.
I see. You have to pay my pound of flesh to do that if I want. So, all right.
And I'm assuming that we'll be expanding the retry logic functionality within Spark, because technically it's possible, just like another abstraction layer.
So this notebook, this is all in Python?
Yes, this notebook in Python, but the same thing would work in Scala as well. Basically, the two Spark languages.
Question: can do all this through .NET?
You know what? I've not used .NET with Spark, so I do not know.
Yeah. I know we've got support for .NET notebooks, and you can do all kinds of stuff like add NuGet packages. I don't know how you would add Spark Connector.
Yeah, that's my question. I don't know if Synapse, for example, because I know like Synapse support .NET notebooks, but I don't know if it allow Spark libraries to be loaded to .NET Workspace, because it has some dependencies. Like I've seen, for example, and this is not with Cosmos connector, but with other libraries. If library is a jar file, like Spark library is a jar file. For example, if you want to use PySpark, it's not always straightforward to use jar library within PySpark. So it sort of need to be natively supported by the workspace to be cross-platform sharing.
Yep. Yep, makes sense.
All right, so let's look at another cool feature of new Spark connector, bulk delete. So previously, Spark 2.4 connector did not support bulk delete natively. And the only way to implement bulk delete with Spark was to use sort of the backdoor of Cosmos TTL feature, where we would enable Cosmos container TTL without the actual value set at 2-1, and then read the documents with basically read their PK ID pairs, which based on some functionality to be deleted, and then update those into data frame, and then add TTL attribute to the data frame, TTL column with specific small value in seconds, and then absort override those documents back into Spark, and then on container TTL would actually delete them. So it was cumbersome to do this, kind of like a lot of reading data, overriding data. So obviously it's like on the bulk deletes was fairly expensive because it's actually absurd, fairly expensive operation. You have to read it first as well. With new connector, now has ability to execute bulk delete operation using new write strategy. And all you have to do is supply data frame with PK and ID unique pairs of the documents to be deleted. So we have two write strategies around it. Item delete all documents, and item delete, if not modified, will delete all documents for which E-tag hasn't changed. So this is one of the examples of the optimistic concurrency control checks we have in Cosmos, where we use an E-tag to validate whether we want to do operations on the document which hasn't been updated by some other process, because this is another sort of the gap in the older connector. It has no knowledge about the E-tag and couldn't do anything. So potentially, while in delete, it's probably not as relevant, but it would be very relevant when you do update. For example, if you want to do a bulk update using Spark, you want to use OCC check because that same document can be updated by some other process. And to show this, let me go to my deletion sample. Bulk deleted, yes. So this is an example of the bulk delete process where we would basically we selecting from those 5 million we loaded, we selecting first 100,000 words into be deleted data frame, and then we basically defining the updating the config to do item delete, and simply, I mean, it may be counterintuitive. We actually using the right format append with the delete config, and then deleting the documents. And based on this, we can say that, well, we recorded the initial 100,000, and then we validated that they are deleted at the end. So that's simple deletion process using Spark, and it's fairly efficient in terms of RU and time.
Is that that's working in the background as it's doing those deletes?
This is actually executing the bulk delete operation from the bulk delete.
Okay, got it.
And it's using that partition key IDs from the main data frame we selected. So even though we select the full data frame, we can actually scope it to partition key ID if we don't have to use E-tag. But if you, for example, delete from, a lot of times what I've seen with customers, they get in the files from like a third party, right? So like some integration, like basically file landed, and then in the file there is a flag. Oh, those records I want to insert, those records I want to update, and those records I want to delete. So like for records you want to delete, you want to actually query those records like originally, right, in order to delete it or update it. But now all you have to do is, because those records will have partition key IDs with them, so all you have to do is let's create the data frame with partition key IDs of the records to be deleted, and just send them to that data frame to be deleted data frame append delete config and item deleted, and it will be deleted in Cosmos.
Got it. Yep.
All right. So another feature with Spark 3 connector. This is a all-app connector feature. This gives you ability to read that analytical store with Synapse Link. The only difference here is that instead of the Cosmos OLTP in Spark Read, we're using Cosmos all-app. This will allow you to read the data from our analytical store if it's enabled on Cosmos container to read that internal columnar compressed analytical store via Synapse Link and avoid using RUs for that operation. It's really useful when you have to scan large data volumes in batch mode to maybe like create materialized view or create subset of data and write some aggregations in batch, because you no longer need to spend RUs on those bulk data reads. This is fairly common. We have a lot of documentation. I'm not gonna focus a lot on this. Another interesting feature, and this is where like there's a little differentiation, is new Cosmos Spark OLTP connector to read change feed. So as I mentioned earlier, we have separate read data source now, Cosmos OLTP change feed with Spark 3.0 OLTP connector, and it's controlled by a set of change feed Spark parameters. First one is Cosmos change feed start from. You have two options, actually three options: beginning, now, or specified point in time in UTC, based on that UTC ISO format we support in Cosmos, which would give you a lot of control on data migration. So for example, you want to do some controlled extraction of data to load subset of data somewhere really cool. One thing to know when you define the specific times, like from point in time or you're trying to restart, if the write config defines the checkpoint location and checkpoint exists, in order for you to resume it, you need to change the location or delete checkpoint, basically clear a checkpoint, similar to, like, for example, if we have a checkpoint in list container for change feed and we want to resume it, we will resume automatically. Will use the checkpoint. If you want to restart or like reset it, you need to clear the list container, and then it will reset the change feed checkpoint in. And then we have two change feed modes. Default is incremental, kind of like our default change feed mode. And we also have full fidelity, which is available in preview if you want to use it.
Wow, that's the very first time we've talked about that in a real way on the show, is our full fidelity change feed. Longtime users of Cosmos will know that we've been working on this for a long time. And it's finally
we know that full fidelity is in preview, and it's also in preview within Spark change feed connector as well.
That's cool. Yeah, we're gonna do a show on full fidelity change feed later this summer when that's out of private preview mode. But yeah, that's a long time coming. That's very, very exciting. It's cool to see that surface through here.
Yes, and then we have a control of how many, basically, that one of the change feed parameters, internal parameters to be exposed here, change feed item count per trigger hint, to define number of items for each microbatch trigger to pull. And
go ahead.
To show the example of this is for validating document count for the load, we used change feed instead of basically reading the data directly from Cosmos to read the same data using change feed and doing the count to validate. So reading the same data using the OLTP connector, 5 million records, took us, say, one second. With a change feed, reading that in those mini batches using OLTP change feed, and we use it from beginning and incremental. Basically, whatever we loaded, we used it. Took us like 45 seconds, so which is not too bad, right? So for change feed, basically processing the feed of data for 5 million records after the load. So that's the way to use it. Let's see what we have left here. Another really cool feature, which really value, is recent addition to Spark Connector is now supporting Cosmos patch operations. That was probably the top feature requested earlier this year, delivered in the regular SDKs. Now we also, Spark Connector team use the same Cosmos Page API to specs to support add, set, replace, remove, and increment within the Spark itself. You define, the way it works, you define your Spark data frame for patch with a DPK to uniquely identify patch documents, and then you define set of patch attributes and values, and use write option to basically persist those down. I included the reference here, and also you can use write patch filter to basically conditionally filter the patch updates. And the quick example of the patch operation, let's say you have the document sample where you have member details with status active. If you want to scan all the documents and replace status to closed, you would define your JSON content, and that document is partitioned by ID. That's why I only have ID. I did not specify a partition key. But ID and status closed, and then I would use write strategy item patch, default operation type set, and then in the column configs, I would define column status, pass member detail status, operation set, and then I'll do write. And this will effectively patch the document with a change in status.
Yep, very cool. I'm glad to see patch in there too. It's definitely another long time coming feature. It's people are loving.
Yes. And to wrap my talk and presentation, I'm including 2 references for the notebook samples I used. The first one is actually pointing to our official Cosmos Spark Connector sample as part of the SDK repo, a link to our documents. And the bottom one is my Synapse notebook, which is adapted to Synapse and has few variations and customizations based on that notebook with those examples I showed throughout the show.
Yep, I got a link up there, and I see you got your link there. And then the other one I wanted to show is, and you can get at the New York City notebook through this one too, but just getting started, this AKMS link here is people can get started just reading docs and clicking through to samples and data sets and other stuff, and learn more. So I had another question. Going back to your Spark OLAP, does Synapse Link read the entire store, or using some kind of index or filtering strategy, I guess, or filtering?
The way Synapse Link reads analytical store, so if you're using the OLAP, if you're using the Synapse OLAP filter, the way it's reading the analytical store is basically scanning the Parquet, the internal analytical store file headers to identify the columns and segments which it can skip and read. So basically, I'm doing Parquet scans, and it's optimized to parallelize, and then within each file header, I know which segments I can skip to do the progressive filtering. With OLTP connector, I'm actually reading the Cosmos directly, and the optimization here that I will link, basically parallelize my read stage to only read the documents based on the filter or a subset of, like, you can define custom query, for example, if you need to read it. But majority, like I would say, we want to use OLTP for writes and updates, and we want to use OLAP for reads, because this will give us that nice balance of, for write and patch operations, we would use OLTP, and for reads, we would use HTAP OLAP, which will not use any RUs, right? Or we would minimize our use for reads because we already spend them on write.
Well, to be clear, no, users can't write directly into our analytical store using that.
That is correct. Yes.
Connector anyway. They could write to they could write Parquet to a blob store format though, and in fact, that's kind of how repartitioning works within Synapse. Is it uses that, and then you create a Spark job to go and rewrite the data out into a new Gen 2 store.
Yes, you're exactly correct. The only way to write to analytical store is to read from analytical store using OLAP and write to
something else,
your own, something else.
Yeah.
Repartition, yes, exactly.
Yep. This is fantastic. Thanks, Sergey, for coming on and talking to us about the Spark connector and all the stuff you can do. And literally, if you're gonna do big bulk ingestion, migrating data, that Spark v3 connector is pretty awesome, I've got to say. I'm with you on the throughput control. Being able to set budget on there is just, I mean, you know, it's definitely something you need if you're working with data or a database that's already out in production, and you don't want to cause issues with performance or anything for those users. So, yeah. Well, thanks again, Sergey, for coming on. Great to have you on again. And thank you. Yeah, thank you, everyone, for joining us. Just some quick announcements here. So, oh, wait, maybe I got a question. Oh, just there. Someone said thank you. That's nice.
You're welcome.
Okay, so yeah, just some quick announcements. So we've got, this is episode 44. You can catch this if you missed any of it or any of the other 43 episodes on, oh, sorry, that's our GitHub repo. Sorry, that's not the one I meant. It's this one here. I'll get my announcements correct here. It's been a few weeks since I've been on the air, so I may be a little rusty, but yeah, check out any of the other episodes we've got, all 43 or all 44 now, aka AMS/CosmosDB live TV. We've also got new user group. We're doing meetups every month now. We're back in the swing of things. So we've got one coming up. Gosh, I think it's this week or soon. I think it may be this week or maybe next week. Check the schedule, but go to this URL and check it out. We're going to do a meetup talking about how you integrate Cosmos DB with Azure Stream Analytics, which is another really cool, fun piece of technology from us. You know, we had Cosmos Conf back in April. Those sessions are all available on demand. Tons of awesome sessions this year. So feel free to go and check out all of our on-demand sessions, or all of our sessions now available on demand, even the live ones. Go and check them out there. So next week is Build, believe it or not, and we're going to be there, and we're going to make lots of announcements for lots of cool stuff. So in case you can't take all the time out of your week to come watch all of our sessions, come watch us next week, and we'll recap all of that for you in 60 minutes or less. So come join us for that. We'll be right here, same time, Thursdays, 1 p.m. Pacific, 4 p.m. Eastern, 2100 UTC, I think, and really early in the morning if you're in Australia, very, very early, or Asia. So come check us out for that. So that's it for us this week. Thanks again, Sergey. Great having you on, and we'll see you, and we'll see you all next time. Thank you so much.
Likewise. Thank you.
Bye-bye.
Bye.